And he said, I thought I was going to fail, but do you see what I'm seeing? And I said, yeah, I see it. He said, what are you seeing? I said, the future.
David Sinclair, welcome back to the show.
Hey, thanks, Tom.
Dude, I'm really excited. I actually want to give the audience a message. I'll look into your eyes, but I'm talking to them. This, I think, is going to be one of the most important podcasts that I ever do, and longtime listeners of my show will understand. For a long time, I was really focused on living forever, and that was the dominant thing I thought about as I mapped out my life. And then about a year or two ago, it started to feel more important to recognize my mortality. And part of it was I had really lost faith that it was going to happen in my lifetime. And I definitely want it to happen. In researching you for this episode, I am regaining belief that we really may hit health escape velocity in my life. And so in the first half of the show, I want to talk about why we age exactly, and you've gotten extraordinarily good at mapping that out with real conviction. And then in the second half, we'll talk about what we can do on an individual level to really slow that down, or possibly even reverse it. So I want people to stick with me, because I'm actually going to start with a story and a quote, and I want to make sure that people know the map of where we're going. So first, the story. On Christmas Eve, I was throwing a little party for my family, and it was a poker party. We had a dealer come, he was 40 years old, and the energy's high, imagine balloons everywhere. It was actually a birthday party. It happens to be somebody's born in my family on Christmas Eve. And I go into the kitchen to get a drink, and my wife runs in and says, we think the dealer's having a heart attack. She was like, you need to get in there right now. And so I rush in to the room where this is all set up, and he's just sitting there holding his head like this. And I said, I don't think he's having a heart attack. I think he's having a stroke. And, you know, long story short, he ends up not surviving.
Oh, no.
And so he was in a coma for, I guess, 5 days, and they end up taking him off life support, and he passes away. And I was like, this guy's 40. And so the question really becomes, how do we get good at understanding where we're at biologically? What is our real age? Not our, as you say, not the number of times that the Earth has gone around the sun, but how old are we really from the things that we can measure, and are they giving us real information? So that's the story. Now the quote. This is you in your own podcast. This is a quote pulled from your first episode. In my lab now, we can control aging very precisely, at will. We can speed it up as fast as we want in an animal and even reverse it. So aging is now controllable. We have the technology to control how fast we age. We can measure that, slow it down, and even reverse it. It's going to fundamentally change the course of human history. I have the fucking chills, man. So that's a big statement. It's a bold statement. And what I want to do now is walk through, what do we know? How do we measure it? And then we'll later get to what we do about it. But I'm a big believer, if you understand the mechanisms, you can make change. What are the mechanisms? Why, for real, why do we age?
Yeah. Yeah, so when I wrote my book, Lifespan, it was a theory about why we age. And when I boiled it down to its essence, I realized and I theorized that aging was a loss of information. So in our body, we have two types of information when we're born, or even when we're conceived. There's the one that we all know about. We can get our DNA read. That's the genome. But there's this other layer called the epigenome. And why is that important? Because if you just have DNA and there's 6 feet of it in every cell, it's just a chemical. It's not going to give you life. What gives you life is the system that reads the DNA the right way. But we've got this chemical that's like a hard disk drive or flash memory that has these letters. And
ATCG.
That's it.
Period.
They're just four chemicals that get strung in different order. Mm-hmm. And the cell can write those down, can build those chains, and that's how we copy the DNA.
I run the risk of taking us off track here, but I'm very curious, where does it get the letters? The enzyme or the protein, enzyme protein synonyms?
Yeah.
Okay. So where does the protein go? Is there a bucket of letters like I had as a kid that it like reaches into and grabs one of the letters out?
There are. Yeah, they're floating around, and then
literally ATCGs
float around. They are.
That's so
we're
weird.
filled with the building blocks of DNA and proteins. One are the DNA bases, ATCG, they float around. And because they're not just floating around, they're buzzing around. And so an enzyme sees probably 10,000 molecules in a second. It's really quick. And it picks the ones it wants. So, okay, I want an A.
And
right.
it's looking at the DNA and it says, you need a C right now. And it reaches out, grabs a C. You need a G now, it grabs a G. That's literally what's happening?
Yes.
That is insane. I cannot believe I've never asked that question. You're freaking me out. All right, keep going.
And how does it know whether it's a G or a C to put down? Because it's copying the DNA. You've got one strand that has the ACTG, and that protein will look for what matches the G. And a G always matches a C, and an A always matches a T. So there are pairs of DNA that make the rungs in that ladder of that spiral, that double helix. But generally, you actually need a template. That's why we have double strands. One of them is a template, the other one you then match to that in the other direction. So it's not like my fly here, which is a zipper that goes up. It's a zipper that does that as it's being built.
Interesting.
But we get that from our parents, right? Without any DNA, there's nothing to copy. Getting back to the memory, there's something I think you'd like to hear, because you're very much into digital and NFT world. It turns out that the best way to store memory now is biologically. In a little test tube, we can store all of human information. And we're built, but humanity is building the machines to write down those letters and store all the world's information in order, and then the readers to get that information back out. So why is that important? Because computers don't last for 1,000 years, and you can't fit all the world's data in a test tube, but technology is pretty much there to be able to do that.
Whoa. Okay, so that's insane. Going back to the reader is that little protein enzyme that's grabbing the matching pairs and building it up. And so all day long, it's just like, here's a half and I need to match that half? Is that the idea?
Yeah, well, there are two things you can do with DNA. You can copy the DNA so that the cell has extra chromosomes that then divide and you have new cells. That's copying the genetic material. But then you can also use the gene, so it's a string of a few thousand of those letters, to make more protein. And so instead of copying it and making DNA, this is where RNA comes in. So we've heard about RNA-based vaccines. mRNA is one type. The cell makes the mRNA, it's called messenger RNA because it's a messenger, and now that message, which might be 1,000 of these letters, floats away from the chromosome, and another machine grabs that and now has its own template to grab not DNA bases, not the ATCG, but amino acids, 20 of them.
So it's programmed to look for these sentences, basically. So rather than an individual letter, I'm here for a whole sentence or maybe even a chapter. It tells me to do something. And is that something to create a new protein? Is that what all of these do?
Mostly.
Okay.
Mostly. You can make RNAs and you can make protein, and DNA, but mostly we're pretty much made of protein. And those proteins are either structural from muscle, or they carry out chemical reactions, making new DNA, making proteins, making lipids, making energy. Without making energy, both of us would be dead in less than 30 seconds. We need to always be making it. It's quite, we're always 30 seconds away from death, as you mentioned. Life is tenuous when you get down to that level. And so what happens with aging is that the ability of the cell to know which genes to read goes awry. Those proteins that would normally turn on a gene that makes a brain cell know to be a brain cell get lost. Those proteins, instead of reading the brain cell gene, will go off and get distracted and start reading a liver gene or a skin cell gene.
Okay, so now here's where I think we have to get away from metaphor, distracted, and now get into, and I know your theory quite well because I've gone through it so many times, but there's a part of it that I don't understand well, and that's the sirtuins. So since we haven't said that word yet today, talk to me or explain what is the when the reading of the information begins to go wrong, what happens that causes that to go wrong? Because it's not like the protein gets bored and starts watching baseball, right? So it's not distracted in that way.
Right.
But there actually is something going on that we can actually see and understand. What is that thing?
Well, so the sirtuins, we have 7 of these genes that make 7 different proteins in our cells, each one. They're very ancient. So the sirtuin actually controls which genes are on and off.
Okay, so the spooling of the DNA?
Yeah, so that 6 feet of DNA is not just flailing around in liquid. That would not be life. What the cell does from conception and before that.
Tell people why that wouldn't be life. You threw that off, but that's actually really fascinating. So if the DNA is just a fully naked strand that can be read in its entirety, you don't have life. That isn't self-evidently clear. Why wouldn't that be life?
Well, you need to organize it very well because we're multicellular. A bacterium doesn't need to worry about it because it's just one cell. It knows what it needs to do, and its offspring are very similar. Our bodies are made of 1 trillion cells, and each one literally is different. Right? Even if you measure an adjacent cell, it's behaving slightly differently. But if you take a brain cell, a nerve cell, compared to a liver cell, it's totally different. But remember, they have that same 6 feet of DNA. So what we need to do as multicellular organisms to survive is to get rid of, not rid of, but hide and compact and silence parts of our DNA that are not useful for that cell type.
So the reader isn't told, your job is to read and recreate liver cells. It's told, read whatever is exposed. And there's some other mechanism that says your job is to hide everything that isn't a liver cell.
And that's a sirtuin.
The sirtuin is the one that hides everything.
Yeah, and SIR stands for Silent Information Regulator. And that was the clue to this whole information theory of aging. It was right there in the name. And what we find is that those spools, so if you zoom, let's zoom up on the genome now, you'll see that most of it is compacted, because most of the genome is not used. We use a few % of it.
The genome is another word for your strand of DNA.
Correct,
Got
yes.
it?
So most of it is bundled up in these little packages.
And when we say it's bundled up, is it put in something?
Yes.
Or is it just squished together in a way that's impossible to read?
It's really precisely packaged. There are 4 proteins called histones, okay, and they make a circular little ball, and they love DNA. So what happens is the DNA wraps around those histones. So you get 2 wraps around one histone.
And it's wrapped around by a sirtuin.
In part, but there are enzymes that do this as well. More machines that grab DNA and wrap it around twice, grab another histone, stick it next to it, and wrap it around more. So it's like spooling. You're wrapping string around a ball, and then you get these balls on a string, it's called. And that, for the technically minded, is called chromatin. And if you take those balls on a string and then wrap those up into bigger bundles, eventually you get what we call a chromosome, which you can see with your eye, or at least with a pretty weak microscope.
This is incredible. We start bundling it. We have the sirtuins. Their job is to silence the vast majority of the information on the DNA. And then we have this other enzyme that comes in, and its job is to read what is exposed. So the information theory is you've got all the possible things. Hey, you're an eye cell, you're an eyebrow, you're a heart cell, you're a brain cell, you're an amygdala brain cell. So it's like all of these incredibly specific instructions. And they're all linked together. And so what we have to do is come up with some very intricate, clean way of making sure that the right information is read at the right time. And the solution that nature has given us is this wrapping of DNA, bundling of DNA, I think is the word that most people use, to make it impossible to read everything but certain sections. But what parts of the bundle are exposed are epigenetics at work, which are based on environmental cues that we give our body.
Well, kind of. Epigenetics refers to all those machines that bundle up the DNA and read the DNA. That's the epigenetic system. It's like in a computer, the code would be one thing, and then all the machinery to read that code, which is the computer, is the epigenome. So, which is kind of complex. You can't say, oh, that's an epigenome protein. There are hundreds, but sirtuins are major players, and they from birth say that this gene needs to stay off because it's a liver gene that's shouldn't work in the brain.
So don't expose it.
Don't expose it. So we've got bundles, 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 a big loop, bundles, bundles, bundles. And some of these loops are really important for when we're developing as an embryo. One of these big loops, it's called HOX, and there are 13 HOX genes, HOX, and they get read in a certain order. The first ones get read and tell the little embryo, this is your tail, which eventually goes away in humans, but we have a tail. And then, oh, this is your midsection, then this is your upper body, then your neck, then your head. That's what this HOX does.
Wow.
And eventually, once you're born, it gets bundled away. Okay, we don't need those anymore. We've built the body. It's got a head and a tail. HOX is there. But when we were looking at older cells in mice and in humans, guess what? That bundle of HOX developmental genes started to open up again because the sirtuins got moved away and did some other things during aging. And now we've got genes that tell us head to tail coming on in our body when they shouldn't. And that's part of the problem with aging, which is genes getting turned on when they should be kept off for decades. And then cells start to get confused.
Does the revealing of the wrong things, that unbundling, does it happen because the sirtuins are not rebundling them? Or are they actively going in and unbundling things that they shouldn't?
Well, what we think is happening is that they physically move away to other parts of the DNA molecule where they shouldn't normally be. That's the distraction. They get called away to do other things. They are very good at handling emergencies. These are emergency survival proteins that they have two roles. One is to make sure that everything's good every day, super optimal health, stay young. But they also, through, I think, evolution, and very early in evolution, their role was to put out the fire. And so they go away. They actually leave where they should so that they're bundling, and for a few minutes until the emergency is fixed, they actually float away, go repair something. So it might be a broken chromosome somewhere else over on another chromosome. They go there, they fix it, and then somehow they find their way back to make sure that bundle is, maintained. But if you keep doing that, and every cell gets at least one broken chromosome every day.
Wow.
And so that's trillions in our body every day. These sirtuins get, I call it distracted, but basically they're doing this other role, putting out the fire, and then coming back. If you do that for decades, eventually some of them, they're lost. They don't find their way back, and these loops of DNA that should never be turned on start to come on.
I may have been wrong then. Maybe distracted isn't a metaphor. They literally have so much work to do, which would make sense. And so now, to actually use a metaphor, you talk about, for people that know what a CD is, that you would get these scratches in your CDs and it would cause the songs to not play right. It was really obnoxious, actually. And that idea of aging, you're going to get these scratches. You're going to get the fires that have to be put out. The sirtuin is going to get busy dealing with breaks and whatever. And so it's got to go handle that, put out that fire, deal with that break. And as we age, there's an accumulation of damage that we do. And so these things are constantly busy. And therein lies the information theory of aging, that the sirtuins are too busy to maintain the integrity of the bundling of the DNA in a given region, which will be different everywhere. But it's no longer holding to the integrity of just be a brain cell, just be a liver cell, just be a pancreas cell. And the readers are only instructed to read what's exposed. And so now, if your brain cell also has a little bit sticking up for skin cell, or tail, or whatever, now all of a sudden you have a dysfunctional cell in your brain.
That's aging, as I see it. That cells lose their identity. We call it X-differentiation, which is an old theory, but this is what we've given a name to it. And so cells, when you're developing from an egg, fertilized egg, to a baby, to an adult, that's called differentiation. Okay? Cells get their identity. The bundles and loops get established. That's youth. That's health. X-differentiation is what happens after that. But then the question is, with the scratches on the CD, Can you get rid of them? Can you polish them? Can you get those bundles that have been exposed to go back to where they came from and reset the age of a cell? And get the brain to wake up and remember, oh crap, oh yeah, I forgot, I am actually a brain cell or an eye cell. So this was the big question that I had after figuring that other stuff out we just talked about, was, is there a backup copy of a youthful epigenome? What does that mean? Does the cell know that that loop that's come out, that it needs to go back in? For that
How did
to be
it know the first time?
well, we inherited that from our parents, that pattern.
Does it memorize that, like, okay, if I'm a sirtuin, am I only floating around a given area? So I know, hey, this is how it's supposed to look. So we get some signal that it's like, okay, we're done growing, head, tail. Bundle those back, and now this is what it should look like forever. And how would it know that?
Well, what the cell does, in part, is it puts chemical tags on regions that need to be bundled up.
Known as methylation.
That's DNA methylation, right?
Okay.
And you can also put methyls, these are little chemicals, hydrogens on a carbon. You can also put them on those bundling proteins called histones, which we talked about. Beads on a string can be modified. But the most important one for long-term maintenance of the epigenome is this DNA methylation. Once you put a DNA methyl, carbon, hydrogen, 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 on a DNA molecule, which goes on the letter C, not all four, but mostly it's on the C, a little bit on an A, then that tags that gene for a certain behavior. Mostly it means shut that gene down and leave it alone. But over time, possibly due to sirtuins moving away, perhaps other things, that DNA methylation pattern across the genome, there are millions of these little tags, starts to go away.
They're dissolved or broken down somehow.
Well, there are enzymes called DNA demethylases that take them off. And they start to do that job when they shouldn't.
Why would we do that job ever? What's the use case for that? There must be one.
Yeah, well, cells that come from stem cells need to grow into different cell types. We have stem cells that grow skin, stem cells that grow new liver.
At all times.
Yeah, we need those. If we get damaged, we need to rebuild. If I cut part of your liver out, it'll regrow into a new liver because you've got stem cells. Our gut is always replacing itself because it's hitting all sorts of things down there. So they're little stem cells. But for those stem cells to rebuild 5 or 10 different other cell types, you need to be able to alter that pattern of DNA methylation even when you're an adult. But that system goes wrong in a way that doesn't make us healthier. It does the opposite. It makes cells more stupid. Cells forget what type of cell they should be, and that's X differentiation. But now the question is, can you redifferentiate? Can you get them to go back to
Isn't
the
that
way
then
they
as
were?
simple as stem cells? If stem cells are the ones that carry that, like, pluripotency of, like, we could become anything, because it sounds like, I mean, to your point about the liver cell, there are already some that are doing this that know, ooh, the liver's gone. I know what I need to do, though, to rebuild it.
Yeah.
And so is that just that mechanism is limited to the liver and the intestines, and therefore it's not doing that job elsewhere? Or
Well, we could have reversed aging just by making all cells a stem cell. We have the technology to do that. That was the 2016 Nobel Prize. Shinya Yamanaka, Professor Yamanaka, discovered that there are 4 genes that if you put into adult cells will erase all their identity. All those loops and bundles will just get erased. Those methyls will get erased. And then you have a primordial, pluripotent stem cell. And any high school student can do that these days, just put 4 genes into them.
That's insane.
Okay, but you don't want to do that because you would become the world's biggest tumor.
That doesn't sound fun.
Yeah, that's not age reversal. That's instant death. And if you do that in a mouse, we haven't done much of this, but there are labs that do this. The mice die within a couple of days.
They just get riddled with tumors.
Well, over time, if you do it a little bit, they get tumors. But if you turn it up a lot, then the cells just forget what to do and the mouse dies, even without tumors. The cells just need to know how to work. So you don't want to do the Yamanaka treatment in a living thing, other than a cell in the dish. But we did stand on the shoulders of Professor Yamanaka because we thought, what if we could find a combination of those genes that doesn't take you all the way back to zero to be a stem cell, but it could take you back to an earlier state that would never go back to being a stem cell, because we don't want to get cancer while we're getting younger. And so it'd be like polishing the scratches on your CD, but make sure you don't do it too much because you'll erase everything. You got to maintain some surface. And it was a few years of work, and I had a student in the lab, brilliant, hardworking guy, Yuan Cheng Lu. And Yuan Cheng was pretty frustrated. He kept putting genes into these old cells in the dish, and they would turn cancerous or they would die. That was one or two outcomes of this binary.
So they would either
experiment.
replicate uncontrollably
Yep.
without remembering when to shut off, or they just
Yes,
give up.
I'm out of here. This is too crazy. But we hit upon a magical combination. And he was literally about to quit his PhD. He said, I can't do this anymore.
Whoa.
I got to change topics. I'm out of here because it's never going to work. David, you're insane. You can't partially reverse aging. It's not going to work. And he had every reason to believe that. I mean, how crazy is it that the cell would remember, okay, this gene here needs to go back to that state, and this gene over here needs to do that. How could there be a memory in the cell of youth? And we didn't know, nobody knew until we did the experiment. And the experiment that I said he should do before he quits was to don't use all 4 of these Yamanaka genes. And in fact, one of them causes cancer. We know that. So it didn't take too much of a genius to say, look, just leave out that gene. It's called c-MYC. And see if the other 3 would work. And no one knew if 3 was sufficient. Most people thought it wasn't. And he put those 3 genes in, and they're called O for OCT4, SOX2, S, and KLF4, OSK. And if you're wondering what do these genes actually do, they make proteins that turn genes on and off during development, right? Starting to see the theme here. And they work with sirtuins and those DNA methyls. All right, so he put in those 3 genes into old human cells in the dish, and they looked fine. They kept growing. They didn't turn into a tumor. They didn't grow uncontrollably, and they didn't die. And then when he measured the patterns of which genes were on and off, they resembled a young cell again. And that was a eureka moment in the lab.
I would say.
We could reverse aging in the skin in a dish. But the real experiment that changed everything was he then made a virus, a domesticated virus, we call it an AAV, and he could now deliver those genes into a living organism, which in our case is typically an old mouse. And he did a very clever thing. He said, I want to work on the eye. His father had a biotech company that is trying to solve blindness, cure blindness. And I said, the eye, are you kidding me? I know nothing about the eye. Blindness has never been cured. You know, how's it going to be possible to deliver this into an eye? Let's just do the liver. I understand the liver. It's easy. We'll just get it in. And he said, no, trust me. I've got the good feeling about the eye. I went, all right, fine. And I've learned over the years, if somebody really wants to do something, let them go do it. And usually they're right. There's this thing in science where you have this gut feeling, but you're not really sure where it's coming from.
Yep.
There's a
Same in business, by the
spirituality, yeah. And I've learned to tap into that, as do students. It's one of the things I teach them. So he took an old mouse. Actually, the first experiment was he actually caused the mouse to become blind. And then he put the virus into the eye, just straight in, turned on his 3 Yamanaka genes, OS and K. And then he looked 4 weeks later at what happened in that eye. And he found out that the optic nerve that was damaged started and for the most part grew back. And that never happens. Optic nerves don't grow back. If you go blind from damaging your eye, you're not going to see again. Same with your spinal cord, same with your brain damage. The central nervous system with nerves in your body does not grow back. It's a fact of biology. And here was Yuan Cheng showing he was able to do that. So why is that relevant to aging? Because when you're very young, if you damage your optic nerve or even your spine or your brain, it can grow back. But we lose that ability as we get older. And here was Yuan Cheng taking the eye back so young that it could regenerate and function. But then he did something very clever. He then put it into a mouse that we gave glaucoma to, so pressure in the eye damages vision. And then he also did it to old mice that had just aged and were blind as well. And he started to cure blindness with his treatment. And we could now measure the age of those nerve cells, and they were literally younger. And those bundles and those loops, we can measure those. And the DNA methylation, the chemicals, we can measure those. And he was sending them back 75, 80% of their age, but not to zero, or not 100%.
Whoa.
So he sent me, I don't know if I've still got it on my phone, but it's recorded in my book, because he sent me this text that said, David, I got to show you these photos. And he sent me an image of the nerve, which is a long strand. It's orange. We stain it orange so you can see it. And the damaged one just looked like there were a few dead cells. But the one that was reprogrammed was bright orange. All the cells, almost all, had survived the damage. And then they started to grow back towards the brain, from the eye to the brain. And you could see it was like a jellyfish tail. And he sent me pictures of that. And he said, I thought I was going to fail, but do you see what I'm seeing? And I said, yeah, I see it. So what are you seeing? And I said, the future.
Wow.
And that is literally what we saw. So now we know you can reprogram other tissues. It doesn't have to be the optic nerve. It can be the retina. It can be the cone cells of the eye. And so we're reversing aging of the eye. That's not hard at all. But we can reverse the age of the liver, the skin. Other labs are doing the spleen, thymus, through this method. So it seems to be a somewhat, if not universal method of resetting the age of the body safely. Safely is the key. And because I started a biotech company called Life Biosciences that wants to cure blindness and other age-related diseases using this method, for the last 2.5 years we've been doing safety studies in mice, and now we're in non-human primates, and those animals are fine. We can blast these 3 genes in the animal and they're fine. They don't get tumors, their eyes are healthy, you don't get malformation of the eye. So it's great. We lucked out, humanity lucked out, that we can actually do this, and that there's a backup copy of youth in each of our cells that can be tapped into.
That's crazy. Do we know what is going on that allows it to realize what it's supposed to look like? What the bundling of that cell is supposed to look like? Because that is what's going on, right? It suddenly remembers, oh, these are sticking out, they shouldn't.
Right.
And how do we go from, it has so many fires to put out that it's just roaming all over the place and it can't get back. How do we sort of give it that breather to come back and go, not only do I remember how to bundle this, but I've got the time to dedicate to bundling it correctly again?
Well, the bundling, it takes a few days, and a week you're getting pretty close. A month you've now got vision back. And then actually, by the way, if you stop the treatment, I didn't know this when we talked last, but when you stop the treatment, it's long lasting. That mouse will still have young eyes 6 months later. And I still do. I want to test how many times can you reset. Because if it's once, it's interesting. If it's 100 times, it's super interesting.
No joke.
And we couldn't do that experiment because the mice were dying from old age with super young eyes. So we got to reset once, but now we're resetting entire mice. And by the way, you mentioned earlier the quote from my podcast, we can actually control aging in the other direction. We now know how to distract and move the sirtuins away. We cut the chromosomes and let them move away. And those gene packages open up the same as aging. So we can make a mouse, poor things, that we can make them age rapidly. Wow. So if you were to come to my lab, I could show you a mouse that's a twin, and its brother, let's say brother and sister, the brother will be 50% older than its sister, but they were born on the same day.
Whoa.
And now we're reversing the age of those mice. Our main mouse is called Lisa, by coincidence, and we're taking Lisa and we're going to rejuvenate her so that she hopefully gets back to being like her brother.
So you sped her up, and now you want to see if you can take her back. Jesus, man. Like, this is, I mean, you said that this is going to be remembered as the moment that human history changed. I mean, but that's crazy. If this ends up working out, like, this is really banana. If you were diagnosed with a serious heart condition tomorrow, would you inject yourself with this stuff? Like, if this was like terminal, they're like, you got 2 or 3 months, B-Raw.
Yeah. Well, so I am a self-experimenter. I think if you gave me a week to live, I'd be on a plane back to Boston today to try this. I mean, there is nothing to lose. It's all about risk-reward, right?
Yeah, yeah.
And we know what the risk of not doing anything is. I'll probably be dead in a week. But that's true for aging too. We know what's going to happen if we do nothing. That's why I take some risk in taking supplements and doing different diets, because I know that the end is not pretty.
Right.
We all are in denial, most of us, that that's going to happen to us. It's just slow motion. If it's not a week, it's a decade or a few decades from now that we're going to suffer. I watched my mother die in front of me. She suffocated to death.
Fuck.
And you know, nobody should go through that as a human being, experiencing suffocation. And I don't think children should watch that either. But the point there is that we're in denial. I mean, I don't want to be a Debbie Downer here, but we don't think about what it's like at the end. It is not fun. It's not typically like, oh, you just go to sleep. Those are the lucky ones. So I'm in a race against time to figure out how to safely reset the age of the body. I would try it, even though I think a lot of people and Harvard Medical School will be upset that I've said that. But realistically, and I'm always honest, I would seriously consider it.
If I was given even months to live, I'd be on a flight to your lab, and of course I would do it after hours with somebody else, so don't worry, but like I'd have to try this. I mean, that's really crazy.
Well, please don't email me. I'm not able to do this. It would be illegal.
I know.
Right?
I'm kidding.
Yeah.
But I'm not kidding at all. No.
Well, on the other hand, there are supplements and there are medicines on the market that show a lot of promise against
and I
aging
think that's
itself.
where we need to go. So what are the things that we can do today to slow aging so that we don't end up needing this, or so that we can live long enough that this goes through all the safety and all that, and it becomes an actual just like standard of care procedure?
Well, before we get into what we can do today, just because it's a continuum of this resetting, what my lab and many others now are doing is racing to find easier ways to reset the age of the body. Gene therapy, it's here, but it's not going to be, mainstream soon. It's always going to be expensive, hundreds of thousands of dollars a treatment. What happens when you can take a pill that will reset your age by a year? Happy birthday, Dad. Take this pill.
Incredible.
And if you reset your age by a year every year, that's pretty interesting.
Escape velocity.
And there are experiments now where people have reversed their DNA methylation age, which we can now measure, by a couple of years. And that only takes a year. So now people are going back, at least their bloodstream is going back younger than that year took them forward.
Wow.
So we are on the verge of something super interesting in humanity. It opens up all sorts of questions about what's the world going to look like for maybe us, certainly for our kids. But getting back to what we can do every day, the main concept that I think we all need to remember is that our bodies respond well to perceived adversity. Right? Those of us who, like to struggle in life, I know you're that kind of guy. It's don't give up, just keep going. Our bodies respond well to that. As long as you're not doing long-lasting harm, an adversity mimetic, which can be don't eat so much, don't eat so often, exercise, be cold, be hot. There are some other tweaks to that. High pressure oxygen therapy is another theme. These put the body in a state of adversity mimicry. And what that does to the body is it says, oh my goodness, I could be dead next week. I could run out of food. I could be chased down by that tribe over the hill or a saber-toothed tiger. I've got to hunker down and become more robust. And don't put so much energy into these other things. Maybe wound healing would be one thing that you could take away from for a little bit and put it into long-term survival. Those are the roles of the sirtuins. Remember, the sirtuins do two things. They slow down aging on the DNA, but they also go and repair things. And if you don't have enough sirtuin activity or enough sirtuin proteins in your body, so in other words, you don't make enough of these little machines, or the ones that you have are pretty inactive and lazy, or don't have enough of the fuel that they need to work, then you're going to age more rapidly. And when the crap hits the fan and you get a broken chromosome, then you're not going to have as much ability to repair that, and you might get cancer. And so what my role or my goal in my lab and in my experiments with my body is to make those processes that respond to adversity super active every day so that it's slowing down the aging process until we have the technology to reset the body and reverse it.
So I have a guess hypothesis on why that would work. Because you've talked about, like, as we get into mTOR and some of your diet recommendations. So basically, there are things like getting into mTOR, which is growth. If you want to add muscle, you're going to have to get into mTOR. You're going to have to give your body the signal to grow, which times are good. There isn't these, adverse things. And great if you're young, great if you're trying to put on muscle, but it may have these long-term consequences. Versus putting your body into this, actually things are hard, now's not the time, let's dial back, let's make sure that we stay strong. And my gut instinct is that from an evolutionary standpoint, that would be a mechanism designed to make sure that you live long enough for times to return to good so that you can procreate. And that you're sort of going into like a semi-hibernation to like outlast whatever environmental problem there is so that you can still be around when the environment changes. Does that ring true for why this mechanism works?
It does, except hibernation gives the impression that you don't have as much energy.
Right.
And that's not true.
I knew that wasn't going to be the right word, yeah.
Not true. People who do what I do have way more energy than someone who sits around and doesn't exercise and eats too much. And our bodies rev up and make more energy so that we can repair the body. We need that energy to fix the DNA and get rid of the old proteins and survive. So think of it as hunkering down, but also having more energy to be able to survive anything that comes at you. And so the converse to adversity mimetics, which is what I try to do, are the abundance mimetics. So you mentioned mTOR. mTOR will sense if you're eating a steak, lots of amino acids, great, build new muscle, that's going to work. But an abundance mimetic is not going to make you live longer. We know that. You can manipulate this mTOR enzyme complex, we call it, let's call it a gene. The mTOR gene, you can manipulate that in a mouse and give it less or more of the mTOR activity. And when you do that, their lifespan changes. And the more you have of it, let's say you've now made it like the mouse is full of abundance, it'll live short, and vice versa. It'll live longer if you turn down the activity of that gene. And you can do that. I mean, we can't genetically engineer ourselves easily these days. And I say easily. You can, but not easily. But what you can do is by eating things that are right, you can make mTOR believe that there's adversity and turn on the repair systems.
All right, so what does this adversity mimetic look like from a lifestyle perspective? So you rattled off a few things really fast, but I imagine diet and exercise are probably going to be two of our most important things, and then knowing some of your views on supplements, I think we should get into that as well.
Right, well I do talk a lot about the tweaks on exercise and diet, but in a very scientific and detailed way. Sometimes I feel a bit silly saying, oh, diet and exercise. Why is this guy who studies the process of aging and the molecular basis of it talking about these diet and exercise? We've known that for decades, but what we haven't known is how they work. We just discovered that just by looking at thousands of people who live long and who don't. And okay, eat that diet, fast that time, do that kind of exercise. We know those people live longer, but we didn't know why. So now we do. So we can tweak it. We can maximize the benefit of those lifestyle changes. But it's worth pointing this out because I think it's empowering. So point one is we can measure our biological age. We can look at the DNA methylation, we can look at our bloodstream. I do that. And some people don't do that because they're scared of learning their biological age. What if it's too high? What am I going to do? But information, knowledge is power. And the important point, number two, is that 80% of your longevity and your health in old age is controllable. And only 20% is dictated by your genes. The genome, the rest is the epigenome that responds to how we live. So that's why I'm all gung-ho for changing your lifestyle, because it could give you 2 more decades of life. And I'm not kidding. If you just do the 5 things that doctors recommend typically, don't smoke, don't overdrink, get enough sleep, get a bit of exercise, and don't be overweight. If you do that versus someone who doesn't, you live on average 14 years longer. And that's just the stuff we know of.
But there gets to be some really interesting stuff that is just now at least making my level of awareness. And I think that some of this speaks to this idea of the adversity mimetic. So when you pointed out that a type 2 diabetic, so diet-induced, lifestyle-induced diabetes, is going to live longer than somebody without diabetes if they're taking metformin. That's insane to me. Here's my hypothesis, and you'll tell us whether this makes any sense. So insulin seems like the problem child here. And so by elevating my glucose levels, I have to pump all this insulin into the system. The insulin is potentially damaging things somehow, some way. I don't understand the mechanism, but its overabundant presence causes damage to the cells in some way, shape, or form. By taking metformin, it's keeping my blood glucose levels down, which means that it's going to keep my insulin levels down, and therefore I wouldn't be doing the damage to the system. So even though I may be intaking the things that turn into glucose because of the use of metformin, I'm actually keeping my insulin response down. So therefore I never get that thing that ends up damaging the system. And therefore, even though I started as a type 2 diabetic, and that's why I'm on the metformin, because of its impact on insulin, I never get the damage isn't occurring at the level that it would, even for somebody who is not a diabetic. Does that sound about right?
Kind of. Kind of. Let's go back to what is metformin. Yeah. Metformin is a derivative of a plant molecule that inhibits the cell's ability slightly to make energy, and in response,
so it's acting on the mitochondria?
Yes. So mitochondria, in high school we were taught they're the power packs of the cell. They do a lot more. They make amino acids, they make fat, they do all this stuff. But we need them for energy. Without mitochondria, we're dead, again, in 30 seconds. And the way, and so I'm drawing this because they're like little bacteria in our cells. They float around and they make energy for us. In fact, like 4 billion years ago, actually only 1 billion years ago, mitochondria were free-floating bacteria that were subsumed by us.
It's crazy.
So we have little pets in our body, and they have their own DNA, which does get mutated over time. The reason metformin seems to work, one of them, is that it inhibits the ability of mitochondria to make the energy. So mitochondria are like a hydroelectric dam. There's water, but in this case it's hydrogen atoms, not water, that gets pumped into a reservoir, which is between two membranes on the outside of the bubble, of the bacterium thing. So hydrogen atoms are really acidic. That's what acid is, lots of hydrogen, protons. And when you get a lot of something, it likes to equilibrate. Remember that you go from a lot to little, it flows. But there's a membrane in between from the high level to the low level. So internal is low, high is outside. And the cell puts this little generator in between that outside space and the inner space. It's the outer membrane space and the inner membrane space. This is what we call it. And this little power generator sits there, and those protons shoot through a pore in that protein. And at the bottom is a generator. It spins. Literally, the protein is spinning at thousands of times per second.
Whoa.
And as it's spinning, it's doing a chemical reaction to make what's called ATP, adenosine triphosphate. Doesn't matter its name. That ATP is chemical energy that we use to live, to make things, to grow. And so what metformin does is that it reduces the ability of cells to make that those proton gradients, it's called. And so you don't build up as much power and you don't make as much ATP initially.
What does that have to do with glucose? Why do you give that to a diabetic?
Well, what happens is that there's a process called mitohormesis. Hormesis is adversity. What doesn't kill you makes you stronger. And mito is the mitochondria are experiencing adversity or perceived adversity. So the mitochondria are freaking out. I can't make enough energy. I don't have enough ATP. Okay? And what gets activated is a protein called AMPK. AMPK is a regulator of energy in our bodies that senses when we don't make enough energy. And what metformin does is it comes in and it activates that AMPK step. And now the cells are freaking out that they're not making enough energy, and in response, they'll make more. And so you have a little drop in energy temporarily when you take a pill, but then the cell rebounds and starts making a lot more energy. And you actually, mitochondria will multiply. You get more of these little bacteria in your cells.
So taking metformin causes replication of your mitochondria?
Yeah.
Okay. AMPK starts, but I still don't know how this ties into glucose.
Well, when you activate AMPK, you don't just make more mitochondria, but cells start to put out a new protein that we haven't talked about, new to this chat, called GLUT4, and that stands for glucose transporter number 4, and it goes to the outside of the cell, right, on the what we call plasma membrane, and it sits there, and now its job is to suck the glucose out from the liquid around it.
So it's no longer waiting for insulin to come around to push the glucose into the cell. It's like, yo, I need glucose to help with this energy creation.
It does, and so it makes more of this protein, but it also becomes what we call insulin sensitive. So the little bit of insulin that you have around, if you're a type 2 diabetic, works better. Okay, you get more insulin receptor, which is the protein that senses insulin. So all in all, what happens to that cell, just to summarize, because it's a bit complicated, is that by tricking the cell into thinking it doesn't have enough energy, it panics, adversity, hormesis, and it'll go now and put the protein on the surface to grab the glucose and be more sensitive to the hormone insulin that tells the cell to suck it in. Why is that good? Because then your glucose levels in your bloodstream will come down and you're no longer type 2 diabetic. There are 2 reasons, I believe, why being type 2 diabetic accelerates aging, why you don't want to have high levels of glucose, and why I try to keep my levels
And you think
flat.
insulin is irrelevant in this chain?
I do. It's a signaling molecule.
Okay.
I mean, over time, your pancreas will suffer because it has to make more and more of it. But that's not what's aging your brain and your muscle and all these other things. What's going on is 2 things. One is that glucose will attach to proteins all the time. It just sticks to it. And in fact, the diagnosis of type 2 diabetes is to look at an abundant protein in your body, in your blood, that you can access at your doctor's office, and figure out what percentage of that protein is stuck to glucose. And that's hemoglobin, right, in your red blood cells. And if you've got 5% or less hemoglobin attached to the glucose, you're healthy. And then you get 6.5, you're pre-diabetic, and higher than that, you're heading towards type 2 diabetes. And that's just all about glucose attaching to proteins. And glucose attaching to proteins messes things up, and they can really not work well. But that's really not the root cause of aging, as I've told you. What's also going on is that the high levels of glucose are making your cells complacent. Tons of energy. Got lots of this stuff going around. The hormones, your brain thinks that it's good. You're swimming in treacle. And so your adversity and repair systems, the sirtuins, they don't work as hard. And so your clock is ticking faster. That's why type 2 diabetics have other diseases.
They don't work as hard, or they're lumbering under the weight of glucose that's stuck to them?
Interestingly, both. Sirtuins will get attached to sugar, but they don't turn on like they should.
They get attached to sugar, or sugar gets attached to them?
Sugar gets attached to them.
Okay.
Yeah. But what's also a real problem is that adversity system is complacent. And so by keeping your glucose levels down, even at a young age, well, I'm not young, but even at a young age, your body will be in this adversity state versus abundance. And that can explain why type 2 diabetics are older when you measure it, and also are susceptible to heart disease, dementia, and even certain types of cancer, and why metformin, the drug that keeps your glucose levels down and activates this mitohormesis defense, doesn't just protect you against type 2 diabetes. By looking at tens of thousands of patients that have taken metformin, they also have lower levels of heart disease, dementia, frailty, and cancer.
It's bananas. It is bananas. Do you take metformin?
I do.
So I'm going to walk through what I think is your ideal protocol minus the supplementation. I don't want to speak to that. I'll let you add any of that other than metformin if you think there's something else people should do. But okay, so a primarily vegetable diet, and a big part of the reason that I think that you recommend a primarily vegetable diet is because of this adversity mimetic versus abundance mimetic, and that because red meat is so rich in amino acids, it gives a signal to the body that we have an abundance, we can grow, and so we're rapid growth, but we're also aging ourselves. So we want to create this, that little bit of a stressor by, or I should say, we don't want the signal that we have abundance. We obviously have to eat well for protein. We're going to need to make sure that we're getting all the protein that we need and all of that. and that you advise intaking vegetables that have gone through a hormetic trial themselves. So like with the wine grapes that are highest in resveratrol, they're often dehydrated, and ones that have fungus on them, I guess, really do well, because resveratrol, I would imagine, is part of their defense mechanism.
It is, yeah.
And then so any vegetables that have had sort of a hormetic push is going to be a good idea. And you give a bunch of examples that I've heard before, like oranges, I guess, if you drive a nail into the bark of the tree, like before harvest, that helps. It's so interesting.
Olives and olive oil, oleic acid. Oleic acid will activate sirtuins, resveratrol. It's not a coincidence that we figured out these kind of foods are good for us separately, but now we understand probably how they're working too. So yes, you're right so far with my lifestyle.
Utterly fascinating. Heat exposure, cold exposure, fasting. That's one that we should probably go into a bit of detail about. So intermittent fasting being a big one. I know that you're doing OMAD, 1 meal a day. I had to ask what that meant the first time I heard it. And you're doing that, you're still intaking a fair amount of calories. I mean, you're in good shape, but you're not withering away. So I imagine that you're roughly taking in enough calories to hit maintenance levels,
right?
But only in a single meal a day. Do you eat like, because I think you eat in a 2-hour window?
I'm not strict about it. I have dinner, and occasionally I break down. I have a little bit of a snack in the afternoon, and occasionally
as needed, kind of.
Occasionally I have lunch with friends. Occasionally I have breakfast. But my best days, I would say probably at least 5-6 days a week, are not eating maybe more than a nut, a few nuts, or a nibble of chocolate until dinner. And then dinner is great. Dinner is a big meal for me.
How many calories in your dinner?
I don't know, but I go to a restaurant and I'm eating multiple dishes. I just don't eat dessert. I steal little bits, but that's it. I avoid sugar like it's the plague for the reason we just mentioned.
Okay, so you advise people to do prolonged fasting if they can. You don't personally, just because it sucks and it isn't fun, and you live your life at a very high level, and so it gets difficult, and I will second that. A 24-hour fast for me is pretty easy. Anything beyond that, my performance begins to decline. Certainly my levels of enjoyment begin to decline rapidly. I've done a 5-day fast, and after day 3, it's like being sick, for me, at least as I've done it. And I'm sure I could optimize and do it better, but I have found that trying to perform at the level that I perform at just has not been possible. Even at 3 days, halfway through day 2, I'm like, I am not as good as I would normally be. I don't have the patience for certain meetings that I might otherwise have. So I have a very similar response to fasting. But my average, when you take it over a week, because I'm slightly shorter on the weekends, my average is about 17.5 hours a day, 365 days a year. Some days it's 14, and other days it's 22. So it just depends on the day. But it ends up, because I tracked it really religiously for a long time, it ends up, on average, all things taken into consideration, 17.5 hours a day. Is there a sweet spot?
I'm similar. I think that's the sweet spot for you and me. There are sweet spots that are different for everybody. Some people like breakfast and don't care for dinner. But you want to be able to...
I'm actually more like that. My last meal is at 1:15 p.m.
Oh, wow, okay. But what you've got now is after lunch, you go all through the night.
Yeah.
You've got that extended period. You want to use the night as a period of fasting because you're not thinking about food when you're sleeping anyway. But also, I'm wondering if you see this too, or feel this. For a few weeks when I started doing this more intensely and actually skipping lunch, it was tough. It's tough for everybody, I think, because we've got ghrelin coming out, and we have to eat something. We're used to eating, but after 3-4 weeks, I didn't feel like eating. In fact, if I ate something, I'd get a little bit woozy or brain fog. And what I saw when I was measuring it, so I've done the Levels Health thing on my arm. So there's a glucose monitor, continuous glucose monitor on the phone, that when you start, your body doesn't know what to do. Hungry, you're losing glucose, you feel tired, you're hungry. But what happens over time, after 3 weeks, is you steady out, and your liver wakes up and learns that it needs to do its job, which is in part making sugar for your body, glucose. But our livers are much smarter than our eyes and our mouths, much. And continuous. Your liver, my liver, if you measure it during the day, I showed you a graph earlier when we were talking, the line through the day is really steady in this zone. And that's why I can power through the day. I don't feel over energetic. I don't feel lethargic. I don't even feel hungry. But there's a really important point, which is it's individual. The other important point is that you need to get through the hard part in the beginning.
Yeah, I don't think people will believe you, nor will they really understand what it means to become metabolically flexible so that you can burn glucose or ketones. And when you do it, though, it changes your relationship to hunger. It's not that I don't know that I'm hungry. It's that it doesn't create any sense of urgency. I'm not distracted. I'm not like, oh my God, I have to eat. It's just, oh yeah, wow, I guess I haven't eaten in a long time. And no one will believe you until they've done it. And I remember when I first went low carb, and this wasn't even me quite going keto, but when I first went low carb, I had a headache. And I was so angry. And I remember saying to my wife, if I had a cookie, I would feel better. And that was true. It would have made me feel better. But on the other side of that was you finally break your metabolic dependency on sugar, and now you can burn either glucose or ketones. Because I used to measure my ketones all the time. And I could predict with pretty high degree of accuracy when I was over 0.5, when I was around 1, or if I was north of 1. And because you feel differently. It's pretty crazy.
Yeah, it's fun to do the glucose monitoring because you can look on your phone and you know how you feel. And I could very quickly see that if I ate normally, like a normal American, a big breakfast, huge spike in glucose goes up over 150, 200 mgs per deciliter. And I'm feeling wired and I've got caffeine in my body. So, okay, I got a couple of hours of hyper. And then I'd have this crash. I'd feel terrible. I need to go to sleep. I didn't sleep well enough. I can't think. I need to get a snack to get back to where I was. And then I look at my phone and I can see that I'm in this crash. I've gone not just, my levels are here. I've gone below that. And now I'm feeling hungry. I'm weak. And then what do? What does everybody do? I need a snack. I need a protein bar or something. And then shoot straight back up. Our days, if on a normal meal, a normal American diet is like that. And it's highs and lows and highs and lows. It's horrible.
Horrible.
You got to break that cycle and just do the and then a little bit in the evening. Food is required. We're not talking about starvation or malnutrition here.
Right.
But Tom, the one thing that I think is really important to tell everybody who isn't doing this is that I'm really lazy when it comes to life. I really am. It's surprising I've gotten where I am.
I know the feeling.
And
very well.
But what I am pretty stubborn. And I like to do things to a point where at least I've satisfied myself that I can do something. But I like meat. I love meat. Vegetables for me were a garnish for most of my life. I love the taste of meat. I would love if meat was life prolonging. I'd be the happiest guy. But I've now learned, that vegetable, at least plant focused, you can eat some meat and fish preferably. It's not going to hurt you. But a carnivorous, mainly carnivorous diet, there's really no evidence that in the long run that's healthy, unfortunately. So I've switched, and I'm very happy with it. I do enjoy a mostly plant-based diet now. Exercise, I freaking hate exercise. I'm Joe Average or worse. I do not like the feeling of being out of breath at all. I like lifting weights because at least I don't lose my breath, but I'm lazy. I have to force myself to go to the gym every day when I do it, which isn't every day, by the way. So if I can do it, anybody should be able to do this. It's just a matter of willpower and getting into the habit of doing that and letting your body adjust.
No doubt. David, this was mind-blowing. Thank you so much for coming on. Where can people follow along with you and what you're doing? Because it's incredible. Well, so the new podcast is a main way to go. And is extraordinary. Oh, thank you. That means a lot coming from you. I appreciate that. So it's on YouTube and Apple. And it's called? Spotify. It's called Lifespan, the podcast. And there's a website if people would just like to find out where to go. But it's on all major platforms. It's, lifespanpodcast.com. On social media, you can find me pretty easily. Instagram is David Sinclair, PhD. Twitter is David A. Sinclair. I like to put out something, every morning or every afternoon about the science that's breaking.
I have access to the world's libraries of information that come out. I get alerts. Most people don't have access or the time to read that stuff. I'm in bed every morning, with some exceptions when I have company, to be reading the scientific literature, and I do that as a service to people who follow me.
It's incredible, incredible. Guys, follow this man, trust me, drink it in deeply. It's incredible. This podcast literally just changed my life. I'm not kidding. That is not hyperbole. I will be making changes because of what you just witnessed. I hope it hit you as hard as it hit me. And speaking of things that will hit you hard, if you haven't already, be sure to subscribe. And until next time, my friends, be legendary. Take care. Peace.